Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known. Hi, I'm Lee Bortons, and it's Wednesday, October 9th, 2024. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss lessons each week from our math curriculum for families with students enrolled in Classical Conversations communities. This academic year, our club's working on a lesson a week together as we prepare to answer our children's questions. So, Kirsty, what do you have for us today?
We are working on lesson 11, curved lines. So I'm excited about this. I always think feels like somewhat of an ambitious week because there's a lot packed in, but Lee has done such a great job of really taking these really big and complicated ideas and really just emphasizing the grammar. And I just want to mention for a minute, Lee, when we talk about the grammar, I know some people hear us say that that it's a grammar year for our students, and they feel like they're maybe missing out on some understanding, or that their Challenge A students maybe want to know why. And I just wanted to address the fact that I cannot think of any other math curriculum that really encourages students to be dialectic and to use their classical skills of learning the way the Math Map does. Every other math curriculum that I've encountered is very didactic, which means it gives you the explanation. And so it may answer that why question that you have in your home. Why does this work? But for you as the reader, it's still just grammar. You're just learning what somebody else has understood. And so by working through the Math Map and using your classical skills of learning, you're really going to be developing your own understanding. And that deeper understanding of the why is going to come in time. So I just wanted to really encourage all of us, because I think sometimes when we hear, oh, it's a grammar year, people think maybe it's babied down or dumbed down in some way, and it's not. Right? The grammar is challenging, and we need to give our kids time to encounter that language, right? We just talked about, right? How do you read set notation with a such that in it, right? We want to take the time to really wrestle with that with our kids. I just wanted to encourage us all.
Well, I'm going to give an analogy too of that. So when you go to read the U.S. Constitution with your child for the first time when they're like 12, 11, 13 years old, you're going to find out they don't know what the words are and they don't understand it. So you can either give up, or you can say, well, that's too much for today, but we're going to learn one thing. Or maybe the one thing we learned was, this is too much today. That we never stop learning. And so we want to encourage parents that studying math doesn't end. It's for the rest of your life. And that might sound discouraging at first, but it won't be. It'd be like, saying, okay, I'm only going to play music till I'm 9 or until I'm 19. And I'm never going to play music again after that. So keep going.
Yes. And we're all in the grammar stage of something, right? I mean, anytime we're learning something new, we're grammarians, and there's nothing to be ashamed of. So we are here. Notice I gave you a little curved line there. And on your math map, go ahead and find the domain that corresponds. So whether you're looking at digits, naturals, or fractions, or whether you're with us and complex, or perhaps you're one of our pilot families in monomials. And so as you find where you are and put a little check mark on your math map, right, it really is valuable to know where we are each week. So we have something new this week. So the first 10 weeks of the year, we're encouraging our communities to play National Number Knockout as their quick warm up. And we're going to shift this week in week 11. And for the next 10 weeks, we're going to talk about 10 interesting integers. Now, for those of you who are in community this year, your tutors have been provided with some sample integers along with some sample questions. And we don't have time to talk about everything interesting about every integer. And so I've chosen a couple of questions that we're going to talk about this week, and I'll switch those questions up as we go through. And I'm not going to use, after today, I'm not going to use the same numbers that we've given to our tutors to use, because we want them to feel like they have something special in their class that is unique for what we've given them. And we're going to come up with a few other interesting integers, because guess what? There's an infinite number. We could do this every day and never run out of numbers. So let's talk about the number 1. And what are some ways that you could represent or communicate the number 1?
Well, the N2K kids love saying anything to the 0 power is 1.
Excellent.
And anything over itself is 1. Anything
Yes.
divided by itself is 1.
Mhm. And then you have all the infinite fractions. You could add a half and a half, or a quarter plus 3/4. And then all those numbers translate into decimals, so or even percent. 75% plus 100%. I mean, plus 25% gives me 100%.
There's also John 1:1.
Yes.
Mhm.
The first thing I
Yep.
thought of was explaining to my kids how many cookies they may have.
One's a good answer.
Yeah, so there's really, right, when we think about how we can represent or communicate the number, right, when we think about it arithmetically, we could say 3 times 2, 5 times 4. We could keep going on and on and on. I could say 1 minus 7 plus 7, right? I mean, I can keep going, and there's an infinite number of ways that I could represent or communicate 1. So that's great. How about if you have students who have maybe been through the math map before, you could challenge them even to come up with things like, what's the probability that it will either rain or not rain today?
And the
Right?
sum of those two in percents or ratios would make 1. What are you thinking?
Yeah, well, the probability that one or the other happens is 100%,
Mm.
right? And so it has to be 1. So there's a lot of different ways we can do that. And so as we go through these next few weeks, I just want to encourage you to think broadly when we do that. How about when we think about geometry? Is there anything we could think about in geometry that we could use to express 1?
Everything like 1 dimension or 1 dot or 1 line, things like that.
Sure.
So concrete items, you could have 1 polygon.
I could. So I could have 1 of something, but now could I talk about a polygon with 1 side?
Not that
No.
I know of.
Hmm.
And then somebody mentioned John 1:1, right? So where else might we see the number in the Bible?
Well, John 17 tells us that all of us here in this Zoom are 1.
Good,
The Lord our God is one.
good. How about, do you see 1 in a prominent way in any other books that you may have read?
There's lots of songs that have 1 in it.
What are some other names we might have for 1?
Um,
Uno.
Uno, good,
Priority.
good,
Healer.
same
good.
thing, that's good, yeah. Just unity.
Unity.
About
Unity.
1.
Unit. Yeah, so there's a lot of different ways that we can talk about 1, right? And we didn't even talk about Roman numerals, tally marks, right? So there's a lot of different ways that we can talk about just the number 1. So we may be tempted when we hear a number to be like, oh, it's not really that interesting, right? But just looking at the number one, we could keep going and probably come up with a bunch of more things that we could say and discuss about the number one. So that's the goal of this warm up each week, is to really just help our students to think about numbers in a little bit of a different way. And so I'm looking forward to doing that over the coming weeks. Oh, and you know what? The other one we didn't use, we talked about the 0th power of anything being 1, but how about the anything power of 1 is 1?
Oh, like 1 to a millionth is still 1.
Yes.
Yeah.
All right. Well, let's go ahead and take a look at our cover for today. And is this work of art familiar to anybody?
Yes. We have done this in our foundations classes in the spring semester.
Yeah, Monet.
And this
So
was
if
in
we-
his lily pad
Yeah, it's lily
in
pad.
his garden. Yeah.
So if this is an artist, right, Claude Monet is maybe an artist that might be familiar to our students from our work in foundations. So you may want to talk about, what do you know about him? What kind of painting did he do?
As we move into challenge 2 in the art, what era of art is he from? And then geography, where did he live?
So we know he was an impressionist, and what was one of the things that he tried to do? If you're familiar with his work, what was something that he did that he tried to do with his painting? What kind of made the impressionists, and then him especially, what was one of the things they were always studying?
The light.
Yes.
Well, the light changed
light.
the way things look.
So there's definitely a connection for us there, isn't there? Because we've talked about how we're in the second dimension, and we've looked at that image of the cross, and we've talked about right, this intersection of Christ with 3D, and so here we see this artist that was all about light. And what does light mean to us in terms of our spirituality?
We've been separated light from darkness.
Good.
Yeah, light is truth.
Yeah, it's like a lack of sin.
How about from our memory work from Foundations, John 1 through 7?
Yeah,
In him was light, and that light was the light of man.
Yeah, right. So we see this, right? So I just wanted to point, right, there's so many different things. We could jump right in and talk about the curved lines, but notice that there's all these themes that we've talked about. We've talked about the light separating it, right? The light separated from the darkness. We've talked about, right now we can talk about Jesus being the light, right? The light of the world. We talk in the Bible, we see how that light illuminates things, right? And so when we're coming into this lesson, that for most of our students, this lesson is not going to have a lot of baggage. Okay, let me say that again. For most of our students coming into this lesson, there is no baggage. They have never seen this before. It is brand new. They are not coming into this with preconceived ideas or fears.
You mean about curved lines?
Yes, about curved lines. For parents, right? This may be, for a lot of parents, this may have been one of the big topics, right? We spend a lot of time in high school algebra on what we're going to talk about this week. And this may be one of the topics that there has some baggage attached to it, right? And so I really want to encourage us not to look at this lesson through the lens of our experience, right? We've seen this before. Maybe we wrestled with it. Maybe we could never read it, and it was just letters, and it was really overwhelming. And I'm just coming into this with that baggage. And instead, I want to encourage us to switch our perspective and go, okay, how might Christ illuminate this topic for me this time around as I see it through my child's eyes?
The other thing is just a general enthusiasm, like, holding the book and saying, I have no idea what this is about, but I sure hope in 3 or 4 years I do. Let's start.
Mhm.
Yeah.
Yeah.
So when we talk about curved lines, right, and we haven't even looked at any of the algebra yet, but think just for a minute about what we've talked about so far. In 1D, were there any curves?
No.
No.
No, we just had straight lines. Well, we only had one straight line.
Mhm.
And now our last 2 weeks, we've talked about lines in 2D. Did we talk about how they might turn or curve in any way yet?
No.
No. So this is a whole new idea, right? So we made it through 10 weeks of the math map, and other than our art, we have not talked about how a line might curve in 2D. But there's a big idea that it can't curve in 1D. So this is something new that we can talk about in 2D. And that's a big idea to share with our students, right? This is something we really couldn't talk about before. But 2D is opening up this whole world and this whole potential for us to talk about something new.
Mhm.
So let's go ahead and take a look at what some of this might look like. So looking at our I squared page and our invention page here, I'm going to encourage you to first look at the top half of the page and where it says constant, variable, function, sum, scalar, product, quotient, exponent, and root. And let's go ahead and define those words based off of what we already know. So who thinks they could tell me what a constant is?
Something that doesn't change.
A number that
Good.
doesn't change. Yeah.
Yep. How about a variable?
A number that does change.
Something that can change, right? Let's go ahead and we're going to skip over function for a minute and let's go to sums. When we hear the word sum, what does that mean?
Addition.
Addition. Now look to the right, and do you see an addition sign?
Yes.
Yep. All right, let's talk about a scalar. When we hear scalar, what does that mean to us? This one might be a little bit more challenging.
Well, I think it works like a coefficient does to a variable. It's sort of like, I don't know though, like a
Yeah. If I said I was going to scale something, what would I do?
Make it bigger or smaller.
Make it bigger or smaller. And so just like Jana said, right, if I have that coefficient, so if we look here where it says scalar, do we see something that looks kind of like a coefficient?
yes.
Letter
Yes.
C.
There's that C, right? So let's go over to the next column. What does product mean?
That we're multiplying things together.
Multiplying. Do we see something here that's a multiplication problem?
Yeah, the f of x times g of x.
Good. And we see it right expressed 2 different ways, one by having them next to each other and the other with a symbol. All right, how about a quotient? What operation does quotient tell us?
Division.
Division. Do we see a division symbol?
Fraction bar.
The fraction bar. Okay. All right, how about exponents? What do exponents tell us?
We're looking for repeated multiplication and we're looking for an index.
Okay, so do we have an exponent?
Yes, we do.
We do. And then how about roots?
It's the inverse of an exponent, sort of.
Good. And do we see the symbol for that?
Yes, the radicand there.
There we go. All right. So notice right, even if we're not really confident with what limits are, right, and we're really unsure about this, there's some things on this page that are familiar to us because we spent all of the first dimension talking about these ideas, right? And your students may even recognize that we looked at this list of rules for limits in lesson 4. And so now we're seeing it here in context. Okay. Now, I just want to, because we don't want to, we're running out of time already, but I want you to just take a minute and compare looking at limits in 1D and limits in 2D. And do you see something that's in 2D and in 1D, and then something that's in 2D but not in 1D?
I see the other way around, so I'm not following.
Okay, sure. So as you're looking at 1D and 2D, what is in both?
It looks like
Points.
it looks like there's straight lines potentially. And what's really weird is I woke up this morning thinking about how lines like this on a plane are a lot like a bent number line. And there's one-to-one correlations, especially if you're looking at curve. So when I look at this now moving with curved lines, I look at it as a bent number line, for lack of a better word, that has correlations depending on which quadrant on the plane that you're in.
Okay, good. Infinity is in both. So I was being a little more literal, and I'm probably not asking the question well, but I want to point out here, look, if you look up here, right, I'm just going to pick this one. X approaches negative c from the left, and look down here, right, X approaches c from the left, right? So we see here, right, at the top, we just are looking in 1D at what is X doing. In 2D, I'm still looking at X, right? So in 1D, I'm saying, what is X doing? I'm just looking at learning this notation, this 1D notation of saying, what's X doing? Here, now I'm saying as, I've added this word as, right? As X approaches, right? So I practiced that in 1D. As that happens, now I'm adding this in. And so notice in 2D, I'm saying, what is my function doing? So I wanted to point that out because I really want us to start to appreciate, right? And you really won't fully appreciate this until you've been through all 30 lessons and start going through it again, because, hey, I helped write this and that was my experience. So I think it's true for all of us. It takes a year. But I want to start helping you see that as we look at things in 1D, right, we're going to build on that now in 2D. But looking at it in 1D helps us to look at just this short piece of it, the smaller part of it that may be more approachable to us. And then as we look at it in 2D, right, I'm building on it. And so for those families and students who maybe are going, okay, this 1D thing, right? What does this mean? Why am I learning this? Well, because it was a layer, right? As I think about, okay, X approaching some number from the left or from the right. Well, now when I look at it in 2D, I go, oh, I'm still looking, right? I'm a little bit familiar with this X thing, but now I'm saying as that's moving, what's happening up and down? And that's what we're talking about with limits. And so that's why we're trying to layer this idea of dimensionality. It's really going to help us to look at things in a more simple way and then build on that. And so I wanted to just help us all to see that that's happening here. And that's one of Lee's goals for these 2 pages, right? Is saying, okay, remember what you looked at in 1D, now we're looking at it in 2D. Or sometimes you might go, okay, we're looking at this thing in 2D, and hey, in a little bit, you're going to see it in 3D. And so where in individual lessons, we're focused on that lesson. These 2 pages, these I squared and I cubed pages, are Lee's attempt to really help you pull some of those ideas together and see how looking at them dimensionally is going to give us some context.
And I want to add, so if you look, there's 1D and 2D. So why didn't I put 3D or 4D or ND on this page? Because this is our summative page of limits. It's because the math's too hard for the level of education that we're trying to achieve. But for those children who are really advanced, you could say to them, okay, so pretend your paper's longer. What would 3D limits look like? And then what would 4D limits look like, if they can imagine that?
All right, so let's go ahead and look at our I-cubed page, our Memoria page. This is another very summative page that is a great reference and a great place to come and start building your Memoria. So let's start by seeing what might look familiar on this page. Are there any things on this page that students may have seen before, even if they didn't necessarily learn the whole idea? They were at least saw these words.
Well, maybe not the labels of the main words, but the words themselves that are going down the left, like constant, we've heard of, line, quadratic, cubic, like they're divided into subgroups down that left side that are a little unfamiliar to me. But that list of words itself, I think I've seen most of those. Not saying I know what they are, but I've seen most of those.
But
And it
that's where we
also feels
start to build. Yeah. Go ahead, Lee. Sorry.
I was saying it also kind of goes from geometric terms to calculating terms. In other words, yeah, cubic or quadratic or a line may feel like a geometry term to me, but exponentiation and logarithms, absolute value, those feel like calculations to me. So they're familiar for different reasons.
Right.
I was thinking my kids who are, we're going through the math map, everything through logarithmic is familiar. Even if they don't fully get it, they've seen it and they recognize that word means something. They probably, like, I don't think my kids at 12 and 13 have any idea about sine, cosine, tangent, even though those are a little bit familiar to me.
Mhm.
That's right. They have now a lot of these things we have seen in 1D, right? We talked about constants, talked about lines. We probably talked about rational expressions, right? In fractions. We've talked about radicals. We've talked about absolute value, exponents, and logarithms. In week 8, we had that look ahead. So we've seen this list before: sine, cosine, tangent, cosecant, secant, cotangent. We probably haven't seen circle, ellipse, and hyperbola. We may not have heard of parabola yet. Quadratic and cubic, we may or may not have heard of in 1D. But a lot of these ideas we were at least introduced to if we didn't go too deeply into this. And so again, I just want to really point out that this is going to be a list you're going to see over and over again. And so you've seen some of the groundwork laid for it in 1D, but we're going to see it this week. You're going to see this in week 13. You're going to see some of this in week 16. You're going to see the whole list again in 17, the whole list again in 18, the whole list again in 25, the whole list again in 26, and the whole list again in 30. Okay, so do you think that this is something that's foundational to mathematics and to the math map?
Sounds like it.
Yeah, this list is going to become really, really familiar to us. And this is some of the information that is going to be really helpful for our students to start to learn. The type of function, that's what's on the left, the far left, that classification, the name of the function, the graph of the parent function. So this is sort of its very basic. If we didn't do anything to it, this is its basic picture of what its graph would look like, its equation, and then what does that reflection look like? And that's going to give a hint towards both what its reflection looks like, but also what its inverse would be if it has an inverse. So not all of these have an inverse, but that would be its inverse if it had one, or its reflection if it doesn't. So the first thing that I would recommend is just having your kids copy these images. Learning the names and copying the images is a great place to start in building familiarity with this. But I just want to encourage you, we're going to come back to this over and over and over again. And that's great, Rachel. I love that your kids are going to remember these from naturals, because this is a fundamental idea that really everything else is built off of. I cannot think, to be honest with you, I have thought, and I cannot think in most of the mathematics that I have encountered, right? And I say this most, right? There's other weird functions out there that are sort of non-algebraic, but anything that could be expressed really algebraically is going to be one of these functions. It's going to be a sum of these functions, a product of these functions, or a composition of these functions. In other words, pretty much all of your algebraic functions, just like the 112 sentences, you take a few things and you build. We can take these and we can put them together in different ways to come up with all of the different functions. So what we've really tried to do is say, this is your basic stuff. Learn this, and then you can start putting them together to create more complicated things. So let's go ahead and take a look at our charts.
Can I ask a
And
question on the I?
yes,
What is the difference on the graph, dotted line and silent, the permanent line?
sure. Those dotted lines are asymptotes. So an asymptote is something that your students are going to be introduced to this week. And I think Babs is going to post a meme that we found on Facebook. So if you're not following the Facebook Math Map page, that might be an enticement to go and check it out, because we found a fun meme to help us understand the asymptotes. But an asymptote is a line that our graph approaches but doesn't cross, in a very simple way, that it represents how our graph can approach that and get really close to it, but never actually cross it. And so we represent those with dotted lines.
And that's what a limit is, in geometry. So I see my limit by knowing where my dotted lines are.
Thank you.
All right, so these charts are somewhat dense, but let's go ahead and take a look and see if you can find some things on here that are familiar.
I see limits, like what Lee said about like the red arrow lines doesn't touch the axis. So
Good.
limits.
So I think it's important to recognize the title on the chart says properties of open shapes, and we're looking specifically at curved lines. So what makes these open versus the chart we just looked at where the conics and this had circle and ellipse on it? So comparatively, I know something about this chart.
Well, even looking at the bottom, the words like constant, line, quadratic, cubic, rational, radical, those might be a little bit weird, but absolute value I know. So there's terms that I understand, and now I can see that they're represented graphically, make a connection there.
So that's a big idea. So I want to encourage us all. So some people may look at this and be like, oh, this is great. This is my happy place. I love doing this. But some people might never have really had this sink in. And so I love what you just said, because you just said, I see some of these names and things like absolute value. And now I'm going, wait a minute, there's an image that goes along with that. And so here's a big idea, that if your students at the end of this week know this, I would count that as a win. That every equation that has two variables, an X and a Y, that all of those have a matching graph. Okay, so every equation that has two variables can have a matching graph, a matching image that describes the equation. Okay, so there's like that to me, like if your students get that, that's like a big deal. Now, the other thing I'm just going to point out here, because I tried to find this meme to share with you all and I couldn't find it. But one of the things that you're going to notice this week is that we use two different notations interchangeably, right? Y equals x squared and f of x equals x squared mean the same thing, right? This y and that f of x are two ways of describing the same value. So I just wanted to point that out because sometimes we say y and sometimes we say f of x because they really are interchangeable. And so we can use, when I say two variables, I might be talking about y and x, but I could also be saying f of x and x, that function variable there acts the same way as the y.
So Kirsty, do we usually say f of x because we actually want to look at a range of numbers compared to when we say y, we're saying, no, we just want the answer to the problem. We're looking at one.
No, I think a lot of times, I don't really know why. I think in my experience, a lot of times we're just saying, well, this is some function of x. And so it just feels more clear to say this is f of x or g of x, because then I can, instead of having like instead of saying different y's, right? Because I might feel like my y's are the same. If I said y equals x squared and y equals x cubed, I might be talking about two different functions, but it feels like that y should be the same somehow. But if I say f of x equals x squared, and then my other function is g of x equals x cubed, it just makes it a little bit clearer. So I think that that's probably why we use that notation that way to describe different functions, instead of having this y that seems like it should be the same, but we're using it in all these different equations. It just gives us a better way to do that. But in that case, we're always talking about what's my y value, that my y value is defined by my f of x or my g of x. So the other big idea, I just want to point your eyes to the top left box, right? Before we get stuck in the weeds of what does this algebra mean and all of these different things, right? Just being able to talk, right? Here's our grammar, just being able to talk about a curve is helpful with our students, right? And so when we look at a curve, being able to say, okay, well, what's its end behavior? What's happening at the ends? What are the ends? Well, the ends literally are where my arrows are pointed, right? What are my outer limits? What does increasing look like? Well, it looks like I'm going up, right? Like I have a positive slope. We've talked about that the last couple of weeks, this idea of slope. How about maximum and minimum? What does that mean? Well, do we know maximum's always usually a high point and minimum's usually a low point, right? Concave up and down might be totally new ideas, right? Because we have not had concavity before because that's something that's unique to curved lines. But we might go, well, okay, so it like things are curving down, maybe that's concave down and then they start to curve up, right? So maybe that's my concave up and maybe I start to match concave down with maximum and concave up with minimum. We see decreasing there. That decreasing gives us that idea of coming down or that negative slope, right? And the one that's on there that might be hard to figure out is that point of inflection. We may not know what that means, but we might guess at what it means because it looks like it's sort of halfway between my maximum and my minimum. Maybe it's something to do with where it goes from being concave down to concave up, right? And then we might be able to find that definition somewhere else in the charts. But just starting there with our students about being able to describe a curve, right, is helpful, right? So you could even practice that at home. Just give everybody a blank piece of paper and describe to them a curve you want them to draw, right? Say, okay, I want everybody to draw something that starts off increasing. Okay, now have a maximum and then start decreasing. Okay, now have a spot that's concave up, right? And let them all draw their own curves that match your description. All right, so before we go on to our page tops, are there any questions from last week where we talked about intersected lines? And we'll have more time at the end for questions also. All right. So let's go ahead and look specifically at what does an exercise from this week look like. So this is going to be a case where we really are going to want to read our instructions. What is it that I'm doing in order to start really understanding? So let's start by looking at the top, and it says that we're looking at exponential functions. Okay, so all the things that we're looking at here are exponential functions. And it tells me to label some points and some asymptotes. And so I may not be sure exactly yet what I'm looking at here. I'm going to look on the left, and I see that I've got my y equals 1, and there's my dashed line that's an asymptote. And I've got this point 2, 2. And so I might look at my next graph, and there's no dashed line. So there's nothing there to label for an asymptote. But this point here is 2, 2. And so I can still fill that in because I can read that off of my graph. And then looking at my third one, right? Oh, I do have an asymptote here. And that is also y equals 1. And this point is still 2, 2. So that's an exercise that's going, right? I can work in columns, but I just wanted to point out that just looking at that top exercise without worrying about what the rest of it means, I can just look at my graph and fill in those points and that asymptote line. Now, as we move down, we're told these three cases are going to represent the case where my base is between 0 and 1. So this might be a great opportunity to remind your students what was that thing with bases and exponents. And so you might want to say, well, remember we had this thing where we said power equals base to an index, right? And so this time I'm talking about this base is some number between 0 and 1. And then here that base is just 1, and here my base is greater than 1. So I might not be sure about much else, but that's what I'm talking about when I talk about base. Now let's look at this line, and it says examine f of x equals a times my base with the x minus h as my index plus k. And then we're told all of our numbers are going to be real numbers. Okay, that might be really overwhelming, right? If you're not familiar with that, that might feel really overwhelming. But notice it just says examine it. And so, okay, well, so this looks like a scalar. I just talked about what base means. This is my index, right? So my index was my x minus h. And then I'm adding something at the end here, this k. And I've been told this f of x could be the same as y. So that's just telling me my vertical. Okay, so I've examined it. So now let's look below that. And now we're given a specific case. And I'm asked to pull some information from that. Well, what I want to do is I want to compare, right? So this position, this plus 1, is the same position as that a. So a equals plus 1. Well, where I had base, I now have 0.5. So my base is 0.5. Then I had x minus h becomes x minus 2. So h is 2. And at the end, it was plus k. Now it's plus 1. So my k equals 1. Then my asymptote is 1. It's actually equal to k in this case. It's going to be sorry, not equal to k. It is equal to k. I'm sorry.
You can also look above on the graph if you don't know
But we're
that.
also looking above, and so we see that it's 1.
Mhm.
And then we're given this point, h, and k plus a is 2 2, 2, which, oh, that's my point up here on the graph. Okay, so now let's look at the next column and see if we can do this ourselves. So again, my a and my 1 are in the same place. So a must be 1. My base and my 1 are in the same place. And that matches what I'm told here, right? That my base is 1. My h, right? X minus 2, x minus h. So h is 2 plus k plus 1. So k is 1. There was no asymptote here. And my point, which I could either read off my graph or from here, is 2. And 1 plus 1 is 2. And then looking at my third column, I'm starting to see what I'm doing, right? I'm just matching. 1 is my A. Now my base is 2. My H is still 2. My K is still 1. My asymptote, if I look up above, is 1. And my point is 2. 1 plus 1 is 2. Okay? So notice I don't necessarily understand everything that I'm writing here, but I'm learning to read this equation to pull out the key pieces of information in preparation for, in future domains, being able to just see an equation and graph it, right? But a lot of the times we don't slow down and say, okay, just read the information. So that's our goal, is just being able to connect the general equation to here's one with numbers put in, and where do those numbers go? The next part says to examine the logarithmic functions as the inverse of f of x above. So I may not remember that, and that's okay. I'm just going to say, okay, I'm going to look at this, and then I'm told to plot and label k plus a comma h. And I might notice, look, this is just a reverse. So it's still 2, 2. In each of these, that point is still 2, 2, and 2, 2. And then my asymptote, I'm going to trace my asymptote. Now, instead of it being y equals 1, it's x equals 1. And here it is again at x equals 1. And I don't have an asymptote here. Now, a student might go, well, wait a minute. This looks like I've just flipped something or I've mirrored something. And so they might start to notice there's a relationship here between my exponential and my logarithmic, and the fact that their graphs are mirrored across y equals x. But I wouldn't push them to get that as they practice this, that's going to come in time, and they're going to start to recognize this just by becoming familiar with these equations.
So when you flip the x and the y, does the whole graph turn 90 degrees to the right?
It's not as simple as that. It's and I don't even know. I'm just going to see if I can change my color of my pen here.
It happens when a lot of times when you have simple equations or straight lines, they do, but they don't always.
So it's not a rotation, it's a reflection, and it's a reflection across this line. And so it feels like it's rotated, but it's a little bit different to that, and we'll talk about that in lesson 18. But it is a reflection. So if I was to take each of these and reflect it across that line, that's where I would end up with that inverse. So that's if you go back to I cubed, and remember I said where it was a reflection across the line y equals x, that's what we're talking about here. And if a function has an inverse, then it will be a reflection across y equals x. But the rules for whether or not it's an inverse are a little bit more specific. we can say everything can be reflected across y equals x.
So this
Okay.
might be a good place to go look at, say, naturals, where there's one graph and it shows both the equation and its asymptote, and its logarithm. And you can see very easily, because it's on the same graph, that it's a reflection. So it really is going to be good for your kids when they're struggling to go look at the earlier lessons, either in the companion or if you have a younger sibling, to see how you got to where you are. And it might be for that week, you go, right, on Monday and Tuesday, you guys are doing naturals again, right? On Wednesday and Thursday, let's see if we can finish this in complex and how much we can do.
That's a good idea. Do you think that for introductory for the littles, like the lower domains, could it, and then if you have a one-room schoolhouse and you have kids that are in fractions and higher, well, the domains to the right, do you think that it would be beneficial for them to mix and match, like the first 4 pages do the naturals and then 5, 6, 7, 8 go back to fractions? Like just hop around domains?
Yeah,
that be
that's called studying, right? When
Mhm.
something's hard, you go find some research something that's easier. So yes, that makes total sense when you're trying to really learn something.
And
Okay.
I've started doing that some with my 13-year-old, but instead of hopping to page 5, 6, 7, 8 in the complex, I actually go to the first 4 pages of
Mhm.
complex, and then we leave the last 4 pages for another, summer break or something.
Yeah. But the other thing is this page feels overwhelming, yet there weren't any calculations. You just had to read it. And that's, again, we're trying to get students to have problems where they can't calculate. And I know that's frustrating because they think that's what math is, but they will never be able to do analytical geometry, which is where this is leading, if they don't read the problem. So I'm hoping those of you on the club see the benefit of just going slow.
Absolutely.
So let's go ahead and look at the next page just because it's a little bit different, similar, but a little bit different. And now we're going to be looking at the power function. And this is a power sum, polynomial functions. And I want to, again, right, so we keep talking about this idea of the power. And so if you want to keep reminding your students, right, let me get this out of the way. There we go. Right. So now I'm just going to write this here. So f of x equals a times x minus h n plus k. So when we talked about exponents, this is what it looked like, the exponential functions. So this was our exponential function. This is our power function. Okay. And I just want to point out, where's my variable for my exponential function?
And the exponent.
It's the exponent, right? It's my index. Where is my, right? So my variable is my index. And here, what's my variable?
Base.
My base. Okay. So now let's take a look at this. And all we're looking at here are these graphs, right? And notice it says examine and classify. And so as we look here, we end up with 1 times x to the 0th power of x. Now I want to point out that we have not expanded this. And so in this case, it works out that these lead terms are going to be fairly simple. We're just following the pattern. So we're not worrying about expanding these binomials. We're just looking at this pattern. So we had 1, the 0th times the 0th power of x. Then I have 1 times the 1st power of x. What do you think is going to go here?
1 times the 2nd power of x.
1 times the 2nd power of x. And how about the last one?
1 times the 3rd power of x.
1 times the 3rd power of x. Okay, so we're just using patterns to look at this. So now let's look at our n. So here n was 0, n was 1. What's n for my next two columns?
2 and 3.
2 and 3. And then a, look at all of these. What's a for all of these?
+1.
+1, right? And so now we get to something where we may have to go and do some looking up. And we could go and look in our chart 11.2 to get these names. Or
On
we
that
could
page. Yeah.
Go to the I page.
go to
Yeah,
the I
the I page.
page, right? And so we had constant, linear. What were the next two names that were in that list?
Parabola. Was it quadratic?
Got it? Mhm.
Quadratic, yep. And you're right, that's going to be a parabola, is going to be the shape. And what was the next one?
Cubic.
Cubic.
And so I think I relate that to a cube has 3 dimensions. So exponents, there are 3 indices are generally related to cubics.
And that's where quad comes from, because a square has 4 sides. So we can help our students to remember. Okay, so now we could look, we went horizontally to look at patterns, but we could also look at these columns and see if we notice anything about our graphs. And we may not at this point recognize a lot of things about our graphs, but what do you notice about our odd numbered graphs and their ends? What do their ends do?
Are you saying ends as an ENDS or the letter N?
Yes. What do their ends, ENDS, do as their ends are odd?
They're pointing in different directions. I mean, one
They
is
are.
and one is way down.
And how about with x squared, where it's even?
Hmm. They're both pointing up.
They're pointing up, right? And so as we notice that as we copy our graphs, right? As we were to copy our graphs down here, that's a great thing to help our students to recognize, right? As they copy those is, oh, yeah, right? That might be a pattern that we're going to look at.
And then just, like we have them trace a lot in the younger grades because hand-eye coordination and copying a graph like this, even an inch down, that's a difficult skill. And if your children are 10, 11, 12, which is the right age for reals, complex, and monomials, they may have a hard time with their eyes still. And so we've made it so it's a step harder, but they're not having to do a whole different graph, which eventually they will.
Mhm. Is there
And notice when we sketch, right? None of mine are perfect, right? So work with your kids on the basic shapes that we're learning here. Don't worry about them being perfect the first time around. Somebody had a question.
Yeah, I'm in graphs 2 and 4. Is there some sort of relation in the fact that one is above the x-axis and one end is below on both of those?
So if you were to keep graphing, and if you want to play with graphs, there's a Desmos is a desktop, it's a website, desmos.com. And you can just put in all kinds of different functions and play around with graphs. And that's actually how we make sure that our graphs are accurate. But you're going to find that if it is odd, right? Think about this. If my X value is negative and I have an odd power, what kind of an answer am I going to get? What will my power be? If my base is negative and my index is odd, what will my power be? Will it
Like
be positive or
-2 cubed. So what's your answer? It's -8. So your answer will be negative every time.
every single time? So if I have an odd index and a negative base, I'm going to end up with a negative power. If it's positive, it's going to be a positive power. So every single time, if my index is odd, I'm going to have my ends going in opposite directions. One's going to go positive, one's going to be negative. But if I have an even power, like squared or fourth, the fourth power, this eighth power, so on, right? What do we know? When you square a negative number, what do you get?
It becomes positive.
Positive, right? And so I like to think of that as my goalposts, right? So I've described it as like, you've got your Saturday night fever or you've got your goalposts. And that's kind of it, right? If it's even, it's going to be some version of this. If it's odd, it's going to be some version of this.
And your straight line at y = 1 is that parabola straightened out, right?
Yeah.
That's so that because all the other ones will always end up going up.
So instead of
Alright.
goalpost or Saturday Night Fever, then you have an airplane flying.
Yes.
The only exception there. But the thing
Alright.
about how you can do that with your little guys, you can do arm movements and you can just, go, even, odd, even, odd. And then later it's 2, 3, 18, 17, right? There's so many games you can play with numbers with kids to keep them quiet and to keep them busy.
All right. So your tutors are going to continue to practice in class every week that logic catechism so that we know our tools and our resources. And so just likewise, we want to reinforce every week your tools and your resources. We want you to feel well equipped and supported as you're implementing the math map at home. So next week, we're going to be looking at polygons. And I think that's a great place where you're going to see where Lee said, okay, 11, there was a lot of content in 11. And especially as our students repeat the math map and they go deeper and deeper into that content, there's a lot. And then we're going to get to 12 and it's going to be like, oh, this feels familiar and this is restful. And we're going to see that there's a lot of these opportunities that Lee really tries to build in for these moments of rest when there's a particularly challenging week. The next week hopefully feels a little bit more restful. All right, so what questions do you guys have? We are at 2 o'clock, but we will, as ever, hang around and answer whatever questions you might have. This might be a first.
I think it's fall break a lot of places. So
Yeah, and
Mine's
so
a
a lot of our leaders are at a week-long training this week that come to the book club. So good. Well, I hope you guys are feeling more confident, and I hope that Kirsty and I are doing a better and better job every few weeks that we improve. And so let us know if there's something we're doing that would be more helpful, because eventually we're going to be going to year 4 of our book club, and we're going to need to have, feedback from you guys on what to do next.
So great as always. Thank you.
Thank you.
Well, thank you. We appreciate all of you because us just talking to ourselves isn't as much fun. We really appreciate when you guys chime in and ask questions because that's what makes it so great. So we're thankful for all of you. Have a great week.
Yeah, you too. Thanks.